So if we want to calculate the area under a curve in rectangular, when the curve is given as a set of points x comma y, you go 1 over and you're about 2 up. You go 3 over and you're about 2.5 up. You go 5 over and you're about, oh, I don't know, 2 3/4 up, etc. So if when you graph the curve like over, up, well, then the way you calculate the area under the curve is you split into rectangles and you multiply the width of the rectangles times the height, where the height is given as a y value, f of x, a function value when x is given, right? So you find the area of those rectangles. And if you increase the number of rectangles to infinity, you perfectly hug the curve and get the area underneath it. Well, if you want to find the area enclosed in a polar graph, you don't plot points by over, up anymore on polar graph. You plot points by angle and how far out, angle and how far out, right? So you plot points differently, so calculating the area will be different as well. So if we take a look at how we plot points, that looks like this, right? Angle and distance from the origin. And that distance can even be negative, right? And that's how we plot the curve. And if we want the area enclosed in that curve, well, then we're going to split that area into little sectors and find the area of those sectors. Now, sector is an actual mathematical word. It means a section of a circle. Now, this is not going to be perfectly circular right here. It's going to be a little different than circle, right? It's along this polar curve, so it isn't like this is a circle. It isn't a circle, so it's not really a sector. But once I do infinitely many of those, more and more of those, if I split it into thinner and thinner changes in theta, I'm going to have less and less error as far as those being sectors versus being sections of this particular curve. So I'm going to minimize that area a lot. So how do we find the area of a sector? Because I need to do infinitely many of those basically areas of a sector. So I'm going to go to slide 14 right now and type in how we find the area of a sector. Well, to find an area of a sector, if the angle, for example, is delta theta, a change in radians, okay, and the radius, for example, is r, is I would take that delta theta and I would figure that as like a fraction out of 360 degrees, right? But I'm not in degrees, I'm in radians. So out of 2 pi radians. So I would take theta divided by 2 pi, and I would multiply that by pi r squared, because that's the area of a circle. So then I get a fraction of the circle's area. Well, look at what's going to happen there. That 2 pi that's in the denominator underneath delta theta, the pi is going to cancel with this pi when you're multiplying. So those are basically gone. So I just have delta theta divided by 2, and I'm going to times that by r squared only. Or put a little bit more succinctly, 1/2 of delta theta times r squared. That gives us our area of our sector. So if that's the area of the sector, look at how the pi's are gone. That's the area of one sector. Now I want infinitely many of those sectors. So what happens is you end up getting a limit of a Riemann sum, and that limit of a Riemann sum becomes an integral. You are going to have to square the r, and you are going to have this 1/2 factor. So if we look at this formula right here, this calculates the area in a polar curve that's given by some r as a function of theta. You square that function of theta. The delta theta in the sector formula becomes your d theta. And then you've got a 1/2 factor in the front. And then you sum that up between alpha and beta, where alpha and beta are two different angles of theta. The angles of theta where your actual graph starts and ends. So this is the formula that we're going to use to calculate the area enclosed in a polar region. It's got to be continuous, non-negative on that interval between alpha and beta. We're going to remember to square the function of theta, which is r. And we're going to remember the 1/2. And there's not going to be any pi's involved in that area formula.